Yep, it's pretty interesting. This is.
First of all, I guess, can we confirm we have a quorum? Okay, this is the SRWA monthly meeting. Thank you all for attending. Going to call us to order. And so, moving on to our agenda items. First is consideration and possible action on approval of the November 6, 2023 board meeting minutes.
So move.
Second.
All in favor?
Aye.
Motion passes. Second item is the general manager's report.
So yes, at this time, we'd like to call Mr. Garza so he can start with the operational report and follow with Mr. Rangel and the financial report.
Good afternoon, Mr. President, members of the board. Right here, right? My name is Jose Armando Garza, and I'll be presenting the production and distribution report for the month ended October 31st, 2023. And this is going to be on tab number 2 of your board binder. And I'm starting on column C. The year-to-date 2023-2024 fiscal year's due-to-date production, it's 200.786 million gallons, for an average of 6.477 million gallons per day. The share for PUV, it's at 171.008 million gallons, for an average of 5.516 million gallons per day. Under column G, we have the distribution for Valley Mud, and that's at 6.320 million gallons, for an average of 0.204 million gallons per day. Under column H, we have the distribution for City of Los Fresnos, and that's at 18.839 million gallons, for an average of 0.608 million gallons per day. Under column I, we have the credit for B&D, and the year-to-date is 4.217 million gallons, for an average of 0.136 million gallons per day. Under column J, we have the allocation for Indian Lake, and the year-to-date is 0.402 million gallons, for an average of 0.013 million gallons per day. Below that, we have the true-ups. As you can see, Brownsville is under by 15.5 million, and Valley Mud is over by 1.28 million, and City of Los Fresnos is over by 14.26 million. Are there any questions on this report?
Nope, no question here.
Okay, in the next page, we have the production and distribution for October 2023. And I'm going to go to column, third column from the left. For the total production of for October was 205.129 million gallons, for an average of 6.617 million gallons per day. And in the column in the far right, we have the water distribution, and that was 200.786 million gallons, for an average of 6.477 million gallons per day. Below that, we have our chemical consumption for October, and that was at 88,000 with $63.71, and the electrical consumption was at 116,059 with 14 cents. In the next page, staff records events that reduce water production. And for October, we had 3 major events. The first one was on the 13th, where we had to repair a fiberglass line break that took 15 hours. But the first try to fix the line was not successful, so the contractor had to come back the next day and continue to work in that same leak. So we had those 2 days on the 13th and the 14th. And then on the 25th, we had a power outage at the well fields that the plant was down for 12 hours for that. In total, in October, the plant was down for 39 hours.
Power outage at the entire well field?
In the entire well field, yes.
Okay.
Yeah.
This is also the second fiberglass line we've had break.
Correct,
right?
yeah.
Okay.
Yeah.
And is there any concern there, or?
Well, this time, actually, this is the first time I've experienced in the microfiltration area, where this was. Most of them has been in the process area, in the RO process area.
Okay.
Yeah.
But not common?
It's maybe a year, in my experience, we maybe experience three leaks a year, more or less. And they're small leaks. I mean, you're talking about drops, but we try to fix them, ahead of time before they get worse.
Okay.
Yeah. The next page, we have basically with the water production and distribution comparing. We're going to start comparing fiscal year 2023 to fiscal year 2024, so we can track the production of the plant. And in the next page, we have the production from the 3 water plants, from plant number 1, 2, and SRWA. That concludes my report. Are there any questions?
No, I have none.
I think that's it.
Thank you.
Very much. Now, I'm going to hold up really quickly. I just realized I forgot to ask for public comments. Do we have any public comments? I assumed you would have yelled at me. Okay, thank you.
Good afternoon, Mr. President, members of the board. My name is George Angel, and I'm the finance manager. I'm going to be presenting the SRWA monthly financials for the month ending October 31, 2023. I'm going to be focusing on the right-hand column labeled fiscal year 2024 year-to-date. Starting off with total operating revenues, those came in at $650,964. To that, we subtract out our total operating expenses that came in at $221,590. Gave us operating income of $429,374. Moving on to the next page, we had net non-operating revenues of $3,127. That gave us income before capital contributions of $432,501. Since we didn't have any capital contributions for the month of October, that was the change in net position is at $432,501. We add that to the net position of the beginning of the year of $22,764,917, gives us a net position for the end of the period of $23,197,418. And there is some supplemental information as part of your packets that show the breakdown of the O&M expenses for the month, if you all have any questions on that.
Any questions?
No question here.
No
Okay.
questions?
Okay, thank you.
Thank you.
Thank you, and then now we're going to proceed with the updates on the well fields.
Remember, as you remember, last week we touched bases on the TDS levels of the wells, and I just wanted to put together some information in reference to you can have an idea of how the TDS behaves or does at the well fields. And as you can see, the higher TDS well is well number 15, this one right here, 7,200 milligrams per liter of TDS. If you can see this area around here, seems to be higher than the area over here to the southwest, which is this number 4 is the lowest well.
So just to be clear,
Uh-huh.
TDS is inversely proportional to what we're seeing on the screen right now.
Right,
So low numbers means high, high numbers means low.
right, correct. Yeah, like for example, number 4 is the lowest at 1,840. And the highest is number 15 at 7,200. But as you can see, this area seems to be higher than the areas in this section, this area right here. So this is just gives us an idea that, like for example, in the future, if we need to expand the well field, if we're thinking about getting lower TDS, might be worth exploring these areas right here to the southwest, right, instead of going northeast. The next slide.
I have a question.
Yes, sir.
Do you, I'm looking at those, and
the wells that are producing the most are the ones that are closest to all this Resaca system down.
On here.
Yeah. And so I was wondering if they're low down here, it may be that with the drought we've had, the aquifer has dropped there.
Correct.
You know, so instead of drilling more wells there, maybe we ought to find out what's going on with that well, because that's the worst one.
Yeah.
And then, or the, well, that one and number 10, 4 and 10 seem to be the low.
Oh, no, no.
Right.
So they're in, higher numbers are good for us in this particular situation.
The what one?
The higher numbers are good for us, right?
No, it's better to have a lower number, a
Okay.
lower
okay.
TDS,
Got it,
yeah.
got it. Nope.
These are lower gallons per minute, right?
No, this is only the salt content at each of the wells, how salty they are, the total dissolved solids. So the lower the salt content, the better. And the lower the salt
Well,
content,
see,
yeah.
I thought that was the production.
No, no,
So,
this
I
is
mean,
the water
I
quality.
just don't know the acronyms and the codes. You know,
Right.
so
Right,
somebody give me a
microsiemens
code
per
book,
centimeter
it'd
is a
make it
very
nice.
specialized
Yeah.
term. I'm assuming that's microsiemens, right?
Microsiemens, right?
Yeah. So the inverse of that is resistivity, ohms, which also is fairly specialized. So yeah, maybe that's something we should think about for
Right.
how to
And
present that.
how it
And
affects in the
TDS,
plant.
by the way, is total dissolved solids. I don't, yeah.
And the higher the TDS, the more energy you're going to be required in order to pass that water through the membrane compared to a lower TDS. We can still treat it, but it's going to require more energy.
Right.
Okay, thank you.
And so this number really, the microsiemens per centimeter, rolls up both our total dissolved solids and our salinity.
Right.
Yeah, okay.
And in the next chart, basically, we obtained data going from 2004 when we started drawing from the aquifer, right? And then 2014, like midway, 10 years after, and then the latest, 2023. And as you can see, some of the wells, or a lot of the wells, are going up in TDS. For example, number 15 being the highest right here, made a big jump, and it's kind of staying there in the high ends. Number 4 initially was down, and it actually went down, and it's staying down for the most part. But we can see like a lot of these wells, the TDS on them have increased over time.
So 2 and 5 and 15 are the worst ones, right?
Right.
And then 19, 18, and 14 are.
Yeah, number
those
4
are
is the
five
lowest.
wells that are. You know, if you could put down there where you've got like 2004 TDS, 2014 to 23, if you could put what that is, when you use those initials, I know you all know all the acronyms, but we as a board member don't. And then
Right.
since this is a public record, somebody in the public reading this, they don't have any earthly idea what it is. So
Okay,
it
yeah,
would be,
you can do that.
It'd be just a little,
Yeah.
put it in
Maybe like
parentheses
salt
or what.
content or something like that.
Yeah. Thank you so much.
Sure. Any other questions?
Know that.
Do you have more data on the TDS measurements? I mean, this is fairly sparse.
Yeah, we have more data, yeah. But for this, the purpose of this slide, we just wanted to know beginning, middle, and the latest.
Oh, okay.
But we do have more data, yeah. Any other questions? All right, thank you.
Thank you. The next item we have is a drought update, as we are still in stage 2 for Brownsville PUB. I'm not sure if your respective agencies have also issued a drought for the area. And do we have here Rene Mariscal to be presenting a quick update on this?
Good afternoon, Mr. President, members of the board. On November 25th, 2023, the U.S. combined ownership at Amistad and Falcon stood at 21.4. That's still 10% lower than where we were last year at this time. U.S. Seasonal Drought Outlook, there you see this one was released on November 30th. What that shows is that in our area, obviously no drought, still lake levels still remain at record lows. Bottom line here, the recent rains have really helped us down here locally, but from the lake level standpoint, we're still at record low levels. Falcon Lake has increased slightly as a result of the recent rains, but Amistad, on the other hand, has remained steady and dropped even a little bit. Thus, the reason for us just being able to maintain same lake levels over the last couple of months. So that's it in a nutshell. We still remain at stage 2. We'll probably continue through the winter, and a lot of it dependent on the rain, and see when we may hit stage 3. If in fact we do.
So Renee, if you can put it back to the graph, I just want to point out what Renee has mentioned is very important. If you look at November, we're at 21.4, and that's for 2023. If you go back to 2022, by this time we had already gotten the rain, and we were already above the 30% mark, almost at 31% there. That's, that 10% drop really makes a difference, but how we're going to go into the season. So if there's no water going into the reservoirs, then there is no end in the drought to go, and likely we'll have to call before the start of the summer or prior to that to going into stage 3. I'm not sure how your respective agencies are doing it, but it's very important. We've been here at Brownsville Public Utilities Board, been announcing to the customers. We've been providing public input. We're going to be providing additional maybe awareness into other type of community involvements and start doing presentations. But it's very important for us to note this. These type of levels have not been seen in a very long time, and we got very close to a lot of the maybe 1998 levels, if some of you may remember how the drought was. And I know that we're talking and we're staging, putting this pinpoint, but it's very important for us to realize the rain and the water did not come in our reservoir system. So.
Has this been statewide? So I know I have friends in Austin that tell me Lake Travis is down, that they now have a gully in front of their houses instead of a lake front.
Yeah, it's definitely statewide. I mean, even though, again, you'll see from a drought standpoint, for the most part, drought-wise, the state is okay, but when it comes to water supply levels, you see that issue throughout the state for the most part.
Is there any way you can show us, instead of the drought outlook, the water supply levels? I don't know if that map exists. I just thought I'd ask.
We'll definitely look for one. Yep.
Worth checking.
Sure.
Might be interesting. Okay, so if we could get you to arrange a few more rainfalls further up the river, I'd appreciate it.
We'll work on that.
Okay, good.
Any other questions?
And that concludes the general manager's report.
Great. Thank you very much, Renee.
Thank you very much.
Are you gonna go out for bids for the Rainmaker?
You want to get in on it?
No. I serve as a board member. I'm not eligible.
You could donate your time. Okay, item number 3, and this is the exciting one, the presentation on the optimization study for current design capacity.
Good afternoon,
And we were given an updated presentation. I
board
think.
members.
Is this the one we're
We should
supposed to
have an
use?
update
Okay.
that we've gotten passed out,
Yeah,
or,
just want to make sure we were looking
right,
right.
there should be an update on the presentation. All right. My name is Judy Adams, and I'm the division manager for the Water Wastewater Operations Division. The SRWA brackish groundwater treatment facility is not meeting its production capacity of 10 million gallons per day and is seeking to improve production capacity and optimization of the plant. On February 13th, the SRWA Board of Directors approved the professional engineering services contract with Carollo Engineers for an optimization study for current design capacity for an amount of $198,776. The optimization study for current design capacity was authorized to proceed on May 24th, 2023. Corello Engineers has concluded the study that evaluates the operational challenges, identifies the reasons that the facility does not meet its nameplate capacity, and makes recommendations to address the production capacity and reliability of the plant. Corello Engineers is present today to present the findings and recommendations of the study. So today we have with us Corello Engineers, the project team. And I want to introduce Haney Mitchell, Senior Project Manager, Tom Secord, Senior Technologist and Membrane Expert, Sergio Espinosa, McAllen Office Manager, and Vanessa Pruneda, Assistant Engineer. So they are here today to present the report that was passed out to y'all.
Thank you. It's good to be back, and this is a really fun project to work on. I like solving problems. It's part of being an engineer. We like to fix things. So this was, part of the process. Judy went over the scope of the study, so I'll skim over that, but agenda-wise, I wanted to give you an update from the last time we met. I'll give you a little bit of a refresher on some of it, and then we'll fill in the blanks with the stuff that was missing, primarily the microfiltration, some of the well field conclusions, and some electrical improvements were missing the last time that we met in October. So scope, again, we were hired to evaluate the performance of the brackish groundwater treatment facility to determine what improvements would be required to meet the nameplate capacity of 10 million gallons per day. A refresher of what the treatment plant is and how it works. You've got groundwater wells and conveyance piping that brings water to the plant site. At the plant site, you have treatment, which consists of the microfiltration step, a reverse osmosis step. Some of the salty water is blended around the RO, so that it's not treated to remove the salt. We add a little bit of that salt back to the finished water, where water goes through degasifiers, and you add your chlorine disinfectants, post-treatment chemicals before it gets stored and pumped out into the distribution system. You also have a concentrate disposal step as well. So just looking at some numbers, this project consisted of two phases of concept. The initial project, built in 2004, was just an RO treatment plant. So we don't see the microfiltration step. And when it was originally built, the capacity was 7.5 million gallons per day. But it was intended to be expanded up to 12 million gallons per day. As over time, it was discovered that the groundwater contained arsenic, and the RO process was not efficient at removing the arsenic. The plant was expanded to add microfiltration. So we see that in the 2015 column here. And some of the important numbers, so the RO process currently produces 8.2 million gallons per day. And instead of a 10 million gallon per day nameplate capacity, it's actually should be capable of producing 10.3 million gallons per day. But to get to that, we need 13 million gallons per day of filtrate from the microfiltration process and upwards of 13.7 million gallons per day from the well field. So as we walk through the rest of the presentation, we're going to look at how these various steps fall short in meeting those needs, in particular microfiltration, well field, the amount of water that we can bypass around the RO system. This graph is data from the plant in terms of years. We've got 2014 through early 2023, or actually mid-2023. And we've got flow rates. I want you to focus on the light blue dots here and the blue line up above. After the plant was expanded with the microfiltration process in 2015, the nameplate capacity is supposed to be the solid blue line, 10.3 million gallons per day. But we can see, most of the time we're not producing that. And in particular, after the COVID pandemic began, we see this decrease in production capacity. It's picked up back again. There have been some corrective actions, but as a whole, plant staff has said that they really can't produce more than 6 to 7.3 million gallons per day. And that's about 90% of the time. You'll see a few dots that come up to the 8 million gallon per day line, but most of the time it's in that range of 6.3 to, or 6 to 7.3 million gallons per day. So we need to figure out why. The first reason is that the groundwater well field is losing capacity. We talked about this last time. The well field is, the wells are plugging, they need to be cleaned. The well field, if all of the wells are running, so we have no wells available for standby, if all the wells are running, it can make 12.8 million gallons per day. And that would result in a nameplate production capacity of 9.6 million gallons per day. And just a reminder again, we need 13.7 to make the nameplate production capacity. So, the well fields are part of the reason. 9.6 with all the wells running, there's got to be some other reasons that plant staff are only making 6 to 7.3 million gallons per day. We're going to look at the MF and the RO as reasons for that. But before we leave the well field, we want to talk about some of the hydraulic evaluations that we've done and the status of that. Last time we talked about this hydraulic model that we'd built and how the well field hydraulic model wasn't matching the existing conditions. The model was saying that the well field should actually produce more water. So that led us to ask questions about valves within the pipeline. And what plant staff has been able to find out was that there are some line valves in the system that are broken. They rotate, and we don't know whether they're fully opened or fully closed, or partially closed, that is. So if they were partially closed, that could be a reason that some of the wells are underperforming. I'll show you a map in a minute to give you some examples of how that could contribute. But we did find was that all the air relief valves were working. So we don't believe that air is a function to restricting the flow rate from the well field. So this is a map of the well field. The squares numbered 1 through 20 are the groundwater wells. If it's a low producing well, it's in yellow. Similarly, we've marked all of the buried valves and the air relief valves. So the air relief valves are working fine. But the buried valves, if that valve is in yellow, it indicates that we don't know if that valve is fully open or not. So the plant staff has ordered the parts. I actually heard that they went out and were able to do one repair. We haven't gotten any updated results on that yet. It was either last week or earlier this week, or actually this is Monday, so it must have been last week that the work was done. But, if we look at two of these valves in particular, this valve here just north of well 13, If that valve was partially closed, it could explain some of the low flows out of well 13 and well 7. Similarly, this valve up here next to well 16, if it was partially closed, it could explain the low flow out of well 16. So in terms of just scheduling to make the repairs, these are the two that we've recommended they focus their attention on first to see if we can fix the low flow problems. Now, some of the other wells are just not producing, and there's no reason why we can't, there's no valve questions associated with them. So what this boils down to in the end is that we're recommending, pending the outcome of fixing these valves, that between 5 to 8 of these low flow groundwater wells would need to be replaced to meet the nameplate production capacity. And in a lot of the cases, hopefully all of the cases, they could be replaced by just drilling a new well 50 feet away from the existing well on the same properties that the wells are currently located at. So the nameplate production capacity shortfall caused by the well field, in the end, it's as low as 0.7 MGD if all the wells are running, to as much as 2.3 MGD. Now, when we add these 5 to 8 wells, we've built in some reliability wells into that number. So if a well goes down, there would be extra capacity available to turn on some wells for standby. Yes.
I have a question. Do we have any way to measure the aquifer?
Yes, you have water level transmitters in each of the wells, and you have flow meters on the well discharge.
I just wanted to, but they're showing the aquifer to be going down?
I don't have a trend of the aquifer levels over time. Well, let me take that back. We know that the specific capacity is decreasing of the well. So that could mean that either the aquifer is decreasing or the well is getting plugged. So outside of that well itself, I can't tell you what the health of the aquifer is in terms of drawdown, but I can tell you that it's either getting plugged or the aquifer is getting drawn down.
My question is, because if we're going to invest in drilling new wells, and the aquifer is not going to produce, we're going to spend a lot of money, and we're not going to get any more water.
Yeah.
So that's why I'd really like to know what the capacity of the aquifer is, because aquifers all over the state have gone down from what and northern Mexico. So
I do think that there is a need for an updated aquifer study, particularly as if expansion is thought about. The studies that have been done were done based on the ultimate build out capacity for the plant as it's envisioned. What I think is encouraging about the aquifer levels is that you have a lot of wells that are producing good capacity, including in this area up here where Garza was showing earlier that the TDS was increasing. So wells 6, 11, 3, 19, 8, those wells are all good producing wells, and the TDS is increasing in that area, yes. But the fact that they are still producing a good quantity of water tells us that it's probably the well plugging as opposed to the groundwater aquifer drawing down.
So I can actually add to that. I had that exact same concern. So we got on the phone with, I believe his name was Kevin Spencer, who did the original modeling for the reservoir. and talk through all the problems with us. And more than likely, what we're seeing is biofouling, localized biofouling, and the reservoir is actually apparently performing better than expected. And some of that is just due to the draw of each particular pump and how far reaching it is. And it turns out it's much more localized than we originally modeled, which is useful, especially as we expect some of these wells to come on in Mexico as well. So, yeah.
The first step to the engineering project that would look at expanding this well, or replacing these 5 to 8 wells would be this hydrologic assessment, so that you could have in writing that, you know, if you replace the wells as envisioned here, you have confidence that the replacement wells are going to produce.
So we would abandon the wells and all the infrastructure on the wells? Or could we use those as backups?
We're actually, the number that we put together for replacing, it would be reusing the pipes that lead to the well house, reusing the electrical transformer that's feeding power to the well house, and reusing the pump that's inside the well. But in terms of the well house, the electrical, all of that would be, the existing would be demolished, and anything that, like a new building would be built over the top of the new well itself.
Those wells couldn't be cleaned once they're out of operation, and clean them and have them to be able to, when the other goes out, put it back here and go back and forth.
I wouldn't plug them. You know, you brought the point up about, you know, what is the health of the aquifer. You could use it as a monitoring well going forward for sure. Again, this could be part of the engineering study to look at, you know, what is the replacement of these 5 to 8 wells. This was my planning level concept, or our planning level concept for that. It could certainly, you know, it'd be a bigger electrical project to have both wells still functioning. But
Well, it might be if we left the poles and everything there, to where you just ran a line and moved the transformer when you were gonna do it, and then move it back. You know, if you're gonna put it out of service and then
What
move
he's
it here
saying
and
is
there.
trying to use the electrical for both wells, only you would use one at a time, but you would have the availability of the original well.
right, and I guess in terms of availability, though, we're also with this 5 to 8 number giving you 3 standby wells that should be good producing wells, giving you good quantity water. Again, this is all stuff that can be revisited in the preliminary engineering study for the replacement of these wells. But
Because one of the things we're charged with is how much it's gonna cost a gallon of water for the new water we're gonna get, or the additional water we need to get up to capacity that it was designed for. So,
yeah, and in terms of getting into the granular level of those decisions, that's beyond the scope of this planning level study.
I understand it, but we
yeah.
gotta have that information so
Yeah.
we can make that decision.
Right.
So that's,
So,
I mean, it's all a rock and a hard place, I realize that, but,
Yep.
you know, the buck does stop here on this,
yeah.
so.
Okay. We also modeled the hydraulics of the treatment plant. The modeling results showed that there is a transfer pump station between the microfiltration and the RO process that requires all 3 of its pumps to be operating in order to convey enough flow for the nameplate capacity. Now, the Texas Administrative Code for any other type of water treatment plant says that you need to be able to convey all of that capacity with one pump out of service. So this would be something that we recommend. It's not, when I say any other type of water treatment plant, it's surface water treatment plants or groundwater treatment plants that are under the direct influence of surface water. So if you had like a riverbank filtration well, and those sorts of treatment plants must comply with this standard, because you have a groundwater source that is not under the influence of surface water, direct influence of surface water. It's compliant with the code, but the intent of the code is, it stands true. You should be able to convey the nameplate capacity with one pump out of service. If one pump were to go down, the impact on the nameplate capacity is 3.4 million gallons per day. So one of the recommendations is this was intended to be built out with this fourth pump. Let's add the fourth pump for that reliability purpose that was, intended in the code, not required for this type of treatment plant. Okay, so we finished the microfiltration study. The last time I was here, we showed you that, in the beginning of the COVID pandemic, there was a decrease in its permeability of the MF membranes. And that was a result of the fact that staffing was reduced and they couldn't accomplish the cleaning that was needed once a month on the MF trains. So as a result of not getting the membrane trains clean, the productivity, the permeability decreased, and that impacted nameplate production. And it's about 2 million gallons per day, but I'm going to show you a few other numbers here. So again, I showed you this picture the last time. This is what the clean membrane, MF membranes look like, and this was the dirty membranes that were autopsied in January of 2022. We recommended a cleaning program that staff has been working on since June, and we see that the cleaning program is helping to restore the permeability levels to that pre-pandemic level of cleanliness. So we're recommending that the cleaning program continue until all the trains cross this 7 gallons per square foot per day per PSI of pressure, this permeability level of 7. So, but even as we dug into the numbers a little deeper, we found that even when clean, the MF system is not going to produce enough flow for the nameplate production. So I've got two different sides to this figure here. On the left, we've got the maximum flow as designed with the maximum allowable flux rate of the membrane. That's how much water can get pushed through the membranes. And what we see on this side is that as designed, the MF system was never going to produce the 13 million gallons per day of net filtrate needed for the nameplate production capacity. So I'll dig into this a little deeper on the next slide, but I wanted to show you where we started in June was with the membranes being fouled and dirty, not clean. We've been slowly cleaning them back, but the filtration rate, the flux rate, was not this maximum allowable of 90, it was 60. We're actually only producing between 7.1 or 5.3 to 7.1 gallons per day. I guess the other part of this I should explain is every day you're backwashing MF trains. So you've got a normal production rate, and then you've got normal production with one train going through a backwash cycle. And the amount of water that you get out in the end during that normal day is 10.6. But you also have 1 day a month where you're going through cleaning on trains. And during that day, you have 2 trains offline. So on that day, the flow rate is impacted to a greater degree. So it's as low as 8 million gallons per day of filtrate flow. So the question is, okay, what's the right number of MF trains? And I added this line here at the bottom, the nameplate production capacity. So the maximum capacity that's achievable with the current 5 MF rack arrangement is between 6.3 to 7.8 million gallons per day, depending on whether or not you're doing this cleaning on a particular day. If we add a 6th train, the flow rate improves. We can actually achieve the 13 million gallons per day needed, except for the days that the racks are going through a cleaning program. So 7 racks gets you the 13 million gallons per day needed to produce the nameplate production capacity. And looking back through the design and talking to staff, it appears that the original project had included 7 trains, but there was probably some cost reductive change order made during construction that took those 2 trains out, which actually derated the plant when that decision was made. So the current capacity shortfall, I think the number I showed originally was 2 million gallons per day. It's actually between 2.5 to 4 million gallons per day as a result of this MF rate. And the higher number being associated with the days that there's a racks going through a cleaning cycle. Okay, the reverse osmosis, this was all the same as what we talked about in October. Some of the RO trains are producing poor conductivity, which is a surrogate for the amount of salt that gets through the membrane. And trains C, D, and F are producing a lot of salty water in their filtered RO water. So the goal here of the blended water being fed into the system is 1,376 microsiemens, which is about a salt concentration of 800 milligrams per liter. So you can see that the trains with good membranes are achieving good salt removal, but trains C, D, and F are having problems. So the poor salt removal is going to limit the production capacity by limiting the amount of blend, that bypass water that goes around the RO. These graphs show that RO trains A, B, E, and G that were replaced in 2022 are producing or rejecting between 99 to 98% of all the salt, whereas, and these dates were all from 2022 to 2023. This graph over here is from train D, one of the bad performing trains, and you can see that the dates here start in 2017 and go to 2023, but the salt removal, it starts at roughly 95% salt removal, but now it's maybe 85% salt removal. So it's time for these membranes to be changed if we want to improve the bypass capacity and help with the nameplate production. We wanted to point out too that even with some of the trains that have new membranes, not all the trains are performing the same. And last time we talked about some of the trains, B, G, and H, had experienced some chlorine exposure, which was negatively affecting their salt removal. So you see trains A and B look very similar to this, or I'm sorry, A and E look very similar to the graph on the left, whereas B, G, and H look similar to this graph over here on the right, where salt rejection is deteriorating. So we want to fix that, and one of the projects that we recommended, we talked about last time, was fixing some piping arrangements on the plant. Right now, because the water that flows from the RO trains to the degasifiers, the degasifier elevation is higher than the RO trains. When the plant is offline, that water can actually flow backwards, and it does flow backwards, and it chlorinates those RO trains. So the piping modification that we'd recommended was changing the elevation of this pipe leaving the building so that it was slightly higher than the degasifiers, and adding a check valve. So this will be one of the projects that you see recommended in the end. Yeah. Okay. If the well field and the MF filtrate water is available, replacing the membranes on trains C, D, and F would result in the nameplate capacity of 10.3 MGD. So the blended water, again, our goal for salt is this 1,376 microsiemens per centimeter. Replacing these three RO trains to a number that mimics some of the other existing trains. It increases the bypass flow rate from 1.3 to 2.1 million gallons per day, which gives us that nameplate production capacity. So the recommendations, we broke these projects into, we call them tier 1 projects. You need to do these in order to restore the nameplate production capacity to 10.3. We have a tier 2 that is associated with projects that help with the operating cost on the plant, but aren't really necessary to restore nameplate production. Here we've ranked them based on how critical they are. So first and foremost, we need to replace the low-producing groundwater wells. This includes 3 spare wells, and depending on the findings of the valve replacements, it's either 5 or 8 wells, and the cost range is $14 to $23 million. We recommend replacing the RO permeate piping to prevent that backflow so that you're not damaging the new membranes that you've got installed there, losing more capacity. We want you to keep doing the microfiltration clean in place process until the permeability levels reach that target of 7. Additionally, there's some problems in the well field. The PLCs, those are the industrial computers that run the wells and report that information and help control the wells remotely from the treatment plant. There's no, or maybe inadequate temperature control on them, so that when it gets very hot out there, they actually lose their ability to function. So this number represents upgrading all of the PLC cabinets in the wells with a climate-controlled cabinet.
What does that mean? Does that mean we're going to air condition the pump well?
Just the cabinet. So imagine this size.
Oh, the cabinet where the
lectern.
the electronic controls are.
Yeah,
Quite common.
Okay.
it's like a small closet.
Got it.
Yeah.
That makes sense. Okay.
Yeah.
Thank you.
The project 5 is adding the 2 microfiltration racks for $4.2 million. Once we've got the water from the well field and the microfiltration, then we recommend replacing the membranes. This spare MF filtrate pump Adding the standby pump is the next project. Plant staff has said that there's problems procuring they're called analog input and analog output cards for the PLCs. Just with the demand and the supply chain shortages, they've actually had periods of time where they weren't able to use, say, a well because they couldn't get the parts quickly enough. So this project, number 8, gives 2 spare analog input cards and 1 spare analog output card for all 20 of the well field PLCs and then 14 of the PLCs. Again, these are the industrial computers that are used to control the plant. I mean, the whole plant runs on automated computers, so you've got to have the ability to replace the spare parts. So, Project 9 is, we talked about this the last time, instrumentation upgrades. It's reasonable to expect that instruments will last, say, 15 years is a good number, and a lot of these instruments are 20 years old. So it's time to replace instruments. Again, these instruments are used to feed into that control system, and the whole plant is run with instruments and automation. So the last 2 projects, pretreatment, chemical dosing, there have been instances in the past where the chlorine dioxide feed during a plant shutdown and startup has resulted in damage to RO membranes, loss of salt rejection. This project would address those shortcomings and automate the process so that it's better protected, less reliant on a quick-acting operator to get out there to do things that will prevent the damage. Similarly, in terms of producing water that meets the treatment requirements that goes out into the distribution system, the same sort of automation should be done to the post-treatment chemicals. These are the chlorine, the ammonia disinfectants that are used to send water out into the distribution system. So the Tier 2 projects, these are projects that improve the operating costs. We identified 2 in particular that, together they're almost $400,000, but they're going to save you between $30,000 to $50,000 per year. So, within a few years, the project is paid for. I would recommend wrapping these into other larger projects, or if you have O&M funds that you could use for that, you could also fund it that way. The last project, and the folks from HAF are here to speak in greater detail on this, is about system-wide reliability, and that's with electrical improvements. And we've got a $14.4 million price tag for that. I think the last time I was here, I talked about damaging the primary electrical equipment could result in losing the plant for 8 to 12 months because of the time that it takes to procure the replacement parts. So this project would address that and some other issues related to standby power. There are some code issues that ought to be taken care of as well. So if you have questions on that one, I'll defer to the folks from HAF that are here with us.
I just wondered if you're putting up a backup generator or what that $14.4 million would be.
Well, wait. Should we ask about the report before we get into the electrical, or do you guys want to jump into the electrical?
Yeah,
we'll jump on you next. Perfect. Very quick. Okay. So any questions about the report so far? Although I do want to say I think your issue of criticality, there's some things I would move around, but small details. I like what you've brought up.
I'm okay. I mean, I'm following it. We'll drill down as we go forward.
Yeah, okay. I was wondering, yeah, so this is a heck of a question, and I understand if you, hedge your bets here, but, so we continued to operate this plant during COVID, pushing it as hard as we could, and we saw that there were some problems that came up. Something, and maybe this is for plant staff to think about as well. If we would have dropped the amount we produce, the amount of water we produce, since we have had to reduce staff by half or more, would that have allowed plant staff to address some of these other issues that they had to kind of put on the shelf, including, cleaning of our membranes? We had that sudden shutdown where chlorine kind of damaged some of our filters. Just a question, and it doesn't have to be answered today, but it would be good to think about. If we, said, okay, we have an event, and more than likely we'll have another pandemic. It turns out everybody's predicting this will be an issue from now on. Next time that happens, should we just cut the plant capacity in half? Something would be nice to know about. So that's one question. I don't think you should answer that, actually, without getting in trouble. Is there any other maintenance we can do on our RO trains?
We recommended doing some cleaning, chemical cleaning on the RO trains. The trains that have the new membranes are showing signs that it's time. So it just needs to be scheduled, and they actually have a budget for doing that sort of routine maintenance. And the purpose of my bringing it up in the report was just to say, hey, the data says it's time. So,
No, definitely appreciate it. So, okay, but that has been addressed. You guys have provided a schedule. Okay, great. Same thing with well cleanings. To prevent future biofouling, we have to clean wells every N number of years, and you guys have given them those recommendations?
The hard part about cleaning the wells is it's if it goes too long, you may never get it back.
Right.
And, there's really more of an art than a science to figuring out whether or not it's too long at this point. The only way to figure it out is to go out there and try on a couple. And if you can get some production back, great. If you can't, then, we got to replace some wells. So.
Okay, but no great set of numbers, no great way to measure it,
It's trial and error.
Fair enough.
At this point. But going forward, I would say, on a 5-year interval budget for going out and doing those sorts of cleans on the wells.
Okay.
Yeah.
And that information has been passed to staff, right?
Not through this report, but I believe they have it through other documents that I've seen. So
I just want to make sure.
Yeah.
Thank you.
Yeah.
I just wondered if we have, I know we talked about well cleaning in the past. I don't know exactly what that means, if they'd go in there with a suction thing and dig out all the sediment that's in the bottom of the well, or how they'd clean it, but that might be something that I learned a little bit about this by living where I didn't have city water, and I had a well that I shared with my neighbor, and whenever the well would go out, it would be a problem. And it required us to drill another well because it was a small hole and there wasn't any way to clean that well. So we'd move over a little bit like you're suggesting. But I don't know, is it possible to clean that well out?
At this point, depending on what the urgency of your needs are, and that's, beyond my scope of figuring out. But what I would do is proceed on a parallel path of, first finish the valve project replacement.
absolutely.
My understanding is that's in the works. They have all the parts. It's just a matter of, they've got 1 or 2 done. They've got 1 or 2 more left to do. So get that done. Let's look at the data and figure out where that stands. From there, a parallel path might look like, it's going to take 6 months or more to go through and clean wells and try a few to figure out if we've gotten anything back. Parallel to that, you could look at, a preliminary design on replacing wells, and that would include that sort of aquifer study that you mentioned. And, you might scope that if you're thinking about expanding the plant. You could scope that engineer that's looking at the hydrogeology to look at, okay, what is the most pumping that we could do out of this well field?
And another issue that I've thought about is, or a possibility, we have a lot of the effluent that after we've gone through, that goes out into the ditch and out. I don't know how many gallons a day that is, but I know it's sizable. And so I was wondering if that effluent could be run back through another system, and because you don't have a well to maintain, you just have an RO system that would.
Ralph, can we get you to speak into the microphone? I
Absolutely.
had a couple.
I'm sorry. The effluent that we discharge,
Yep.
I know it's very clean because I've seen it's clear. There's fish living down there in that ditch. So I was wondering, I was in Singapore where they took raw sewage and made it into bottled drinking water. So I know that there's ways to do that, but now the cost per gallon is pretty high.
Yeah.
But I was wondering what it would, if it was feasible and might be more economical to treat more of that effluent a second time to produce more potable water and still be able to discharge into that
Drainage canal.
drain and be legal and not have any problems. Just something I was thinking about, and I said, I know they redo that, and I realize that that's not the direction you've been going in, but I've just, this is a good time to talk about these things.
If you were looking like in terms of like a water supply master planning effort, where you were going to evaluate expanding the plant beyond 10.3 MGD, that would be a good exercise to go through to look at, what would be the supply alternative if if you have the need. What are your supply source alternatives? And you'd go through that thought process with that sort
Well,
of.
considering the cost of drilling new wells, if we're going to drill 5 new wells, which is $15 or $17 million, or maybe more, maybe it's 30. I don't know exactly what it is, but I know it's a sizable amount of money.
Yeah.
If we just did a once over, not drill down to the very bottom of the project, but just what it would cost to preliminary,
Yep.
what
That
it
would
would
be- yeah.
cost to do that. It might be we're leaving water on the table.
A supply planning project that evaluates your next increment in capacity could address that question, yes. We're doing direct potable reuse projects like that, one in El Paso that's in the final design stages. And then we have got another one that's 30 million gallon per day production for City of San Diego.
So the question's been asked before.
Yes, yeah.
Okay. So,
But usually, like for San Diego, they're looking at that as an alternative to seawater desalination, which would be more expensive than the well field project. But it would be, you've asked a good question. A a study could answer that question.
Just maybe even a small unit, so that you could get, a smaller scale of doing it and not build a 1 million gallon a day RO system, additional RO system, but maybe, I don't know, 10,000 gallons a day or something that would just give us a
With-
test well.
Yeah, the other thing that's in the back of my mind is I'm thinking there's certainly a cost question here. There's also a customer question. With
There's
all
what?
of these direct potable projects, there's a lot of public outreach that's done. They've rebranded the effluent treated to drinking water. They call it pure water because the San Diego project back in the late 90s, early 2000s timeframe was originally killed when the press started calling it toilet to tap. So they've gotten past that at this point, but again,
Well,
I think
locally,
there's...
I understand what you're talking about because we have never discussed this, but I'm not talking about going to the treated sewer water, but the RO bypass that what comes out of the RO that goes into our discharge because there's no sewage involved in that at all. That would just be, it might have a little higher content of salt, so it might require more RO and more RO equipment and maintenance, but it might be cheaper or more economical, considering we're going to have a source of water, to treat that water, and it wouldn't be it wouldn't be sewer effluent. It would be just a bypass from the RO system, because I don't know what the percentage is. I've stuck my hand down in that ditch where the thing is at the bottom of those stairs and touched it, and it didn't taste salty. So I figured it really wasn't too awful. So just an idea. I didn't die either. Anyway, just for thought, food for thought.
Definitely something to chat about. Okay, so we went through that. We have Half and Associates, and they were going to talk about their half. Sorry, the electrical aspect.
Thank you very much.
Also, yes, thank you.
Members of the board, Mr. President, good afternoon. Gabriel Benavides with Half Associates. So just to give you some context of what the cost estimation entails, we've given you some bulleted points up there. We have the electrical system study code requirements. So we did a very detailed walkthrough of the site, and we identified some potential improvements that will resolve some of the code issues that we identified in our walkthrough, which entails mainly a arc flash labels. So the equipment, the electrical equipment currently does not have arc flash labels, and so we recommend, as part of the study, to conduct an electrical power study that identifies what these arc flash incident energies are, which will promote a safer environment for certainly for the electrical people working on the electrical equipment and the operators. It's mainly a label on front of the equipment that says the type of protective gear that an electrician needs to wear while working on the equipment, on the electrical equipment. That was one item that we identified. The second item were general maintenance and repair opportunities that we saw for improvements, mainly having to do with enclosures that were either opened or needed improvements to gasketing to protect the internal components of the equipment. That was throughout the water plant and also the wells. So that in the breakdown of the cost in the study, you'll see those cost estimates in there. The third item is standby power upgrades. So before I get into recommendations, I'll give you just a brief what do you currently have at the water plant? So currently you have a radial electrical system. What does that mean? That means that you have one electrical utility line coming into the facility, okay? So that utility line connects your utility transformers throughout, which distribute power to the electrical equipment that powers the electrical loads at the plant. If there were to be a fault, whether it be an arc flash fault or a short circuit fault, at any point in the system, there could be, operational issues, and you could be out of commission. Okay, that was the main opportunity for improvement that we identified in the study, and we're going into the Class 1 electrical system reliability, which is a standard that is published by EPA. We're recommending to provide some redundancies to the utility lines, having a standby utility line, so 2 utility lines with redundant transformers throughout. And then that redundancy follows through to your electrical equipment inside the facility. So in other words, we're creating 2 trains of electrical systems. So if one train were to be down for a fault, you have half of the loads or half of the plant also with power, so you can continue operations. Okay, so that's part of the breakdown in the study as well. Standby power upgrades, currently you have 1 generator that backs up the plant. It's a permanent 1 megawatt generator. So there's means to connect portable generators throughout the other, there's 3 sections of the plant. The other 2 sections have a means to connect a portable generator, but everything's manual operated. So what we're proposing is to implement a backup power system that is automated with automatic transfer switches, so that personnel really don't have to manually operate these systems. If there's a power outage, a utility outage, the transfer switches have the mechanisms to transfer power from utility power to backup power. Okay, so that in your report you'll see the breakdown of that option to implement backup power, permanent generators with automatic transfer switches, and then we take another step into the Class 1 electrical system reliability, which is to create 2 trains of electrical distribution within the plant. And so that's also detailed in the study for you. Okay.
The trains that you're talking about, they would be the demand would come, we would be drawing from PUB's power. We wouldn't be having the redundancy come off of the grid.
The redundancy would be within the facility. So, for example, let's say we have 4 high-service pump stations, 5 high-service pumps, we would put 2 pumps on one train and the other 2 pumps on another train. Okay, so if we were to have a failure on one of the trains, I can still run the plant, half of the plant, on one side of the other train, electrical train. Yes, sir.
Okay, but see, I wasn't following what you were saying. I was thinking that you were putting all this power in. Okay,
No, we're not increasing electrical demand. We're just essentially creating redundancies in the electrical systems so that it's more reliable. And we're promoting resiliency. If there were ever an arc flash or a fault with any point in the system, you have at least half of the plant that you can continue operating, because you have two trains, half of the plant on one train and the other half of the plant on the other train.
And what was the risk of arc flash? I mean, how many, locations, or did we identify as a possible arc flash location? Like, where do we have that high voltage?
So arc flash exists in any electrical system, anywhere. It is a risk, but the code tells us that we need to identify what that risk is and then label it on the equipment. So that's really a study that an engineer can do, and they can study the different characteristics of the system, and then eventually identify what that risk is and label the equipment.
Okay, so I'm trying to understand, I guess, what the risk is to our equipment. And so if you have an arc flash, which would be unfortunate, but let's say we have one, we bring down half the plant or we bring down the whole plant, you're saying that, you know, doing this, we're able to, let's say the year it takes to get replacement parts, run half our plant instead of bringing the entire thing down for the year?
Yes, sir.
Got it.
Yeah.
So that's the cost benefit there. Okay.
That's a cost benefit, and essentially what this does to your operations is, we call it in the industry stiffen the electrical system. So we make it more reliable by doing this. Any other questions? Thank you.
I think we're set. Thank you very much.
Thank you.
Thank you.
Thank you.
Well, okay, so now we'll move on to the last item, discussion for the next board meeting, date and time. And believe we're going to
Well,
do
this is the
January
last-
1st. Everybody's okay with that? No.
No, I don't think so.
So this is the last meeting of this year that we have for SRWA, and so right now, the next scheduled meeting time is January 8th, 2024. We'll go ahead and provide you a schedule, we provided you a schedule for the next one is January 9th, 2023, and we have a schedule through January 8th, 2024. And so, I'm getting confused, I'm so sorry. I thought I had the calendar in front of me, and my apologies on here. So our next meeting is January 8th, 2024. There we go. And so the next meeting time, we'll go ahead and give you the 2024 schedule. So any questions on that or any topics?
We're talking about having the next meeting on the 9th of January.
And we'll have it on the 8th. 8th happens to be the next, the next regular schedule would have been on the 1st, but that's a holiday, so that's why we're on the 8th. Monday, the 8th.
The 8th is a Sunday.
No.
Oh, excuse me, I'm sorry, I'm in 2023, I apologize. I pushed the wrong way on
Yeah,
my calendar here, I'm sorry, just a minute. Let me get over here, I'm sorry, Marilyn. That was, okay, the 8th, yeah, okay. Got it. I had already put it on my calendar. So if that works, that works for me.
Okay, so nobody wants it January 1st?
Okay.
No.
Okay, good.
Any items that we're going forward for the next meeting or any things of concern, things that we've covered in the last year that we want to bring back?
Yeah, I'd just like a little bit of a discussion from, just if we reduced our operations 50%, would that allow us to operate,
You're talking
at
about
the same level?
staff levels operations, okay?
Or, is it just, we're running the plant, it's either on or off, binary, we require as many people as we require.
Yeah, I'm not sure, but we'll go back and look at what staffing plans were there for COVID, if those were run or what it was, then we'll have a presentation.
I would also like to see if we have a plan for the maintenance and the cleaning of the wells. I don't know if that's something that we have already in place or we're planning to do this something that way we can prevent and have an update on that.
We'll bring something back, and one of the things that we had discussed here, we were writing about making it a priority on the valves system.
Yes, and of course, an update on how the valves replacement had performed. And also plans, so we have this great study. What are our plans with this? Especially because I think some of the study findings need to be implemented sooner than later, the backflow prevention, the probably pretreatment chemical flow dosing. Just those seemed a little more urgent, a little lower dollar, but, anyways, anybody else? No?
That's a
Okay,
good
so
place to start.
we'll have a heck of a meeting next year too. And we'll all forget that it's 2024 and we'll keep saying 2023 for at least 2 months. Okay,
you.
well, if nobody has anything to add, we're going to call this meeting to a close. Thank you very much.